Переходим к следующему докладчику. Сейчас будет Артур Франц.
Our next speaker, Arthur Franz, he will talk about the generalization in machine learning.
So, hello, welcome to my talk. I would like to present the talk about generalizing machine learning, which is an important topic on the way from narrow AI to general AI. And the question is how to do that, and it's not clear how. But it would be very important to achieve that because machine learning is a very successful part of AI. Now, there's this AGI trilemma, how I call it, from the perspective of computational efficiency. So classically in good old-fashioned AI, you had this approach when you know the task and you hard-code the features and you build the program around the task. And of course it will be efficient then, but everybody knows it's narrow, it doesn't generalize well. If you try to use the same algorithms for a wider set of tasks, you will end up getting the curse of dimensionality, as everybody knows. So it will be computationally inefficient. The other option is to parameterize a large class of distributions and optimize some objective function, which is often what machine learning approaches do, and this has been proven effective and also efficient for a wide range of tasks. But again, generalization is difficult. For example, consider you want to describe a circle, right? A circle has a simple symmetry, and it's a simple regularity. But if you choose a class of functions that it's not fits well to the world that you actually try to describe, for example, a polynomial. Circles are not subclasses of polynomials, right? And if you fit a polynomial, as you see in the picture, to a set of data on a circle, you will get good interpolation, but you will get bad extrapolation. And this is also known as the out-of-distribution generalization problem in neural networks. That's what they suffer from as well. So you basically, if you only generalize well between the data points that you have trained the network on, but you have bad generalization beyond that. And the third option would be train a universal program, or use a universal program search to go through all programs. This will be general, but inefficient, of course, because there are too many of them. So how can we be efficient and general? This we could say that this is the central part of AGI, actually, the central problem of AGI. How to build an algorithm that is general and efficient at the same time. And in order to attack this problem, we have developed this theory of incremental compression, and which says that, okay, let's build something that finds a property of the task on its own and uses that property to narrow down the search space. And once you have done that, you can find another property that narrows down the search space even more. And then you go narrow down more and more until you find the solution. That's the idea, and we have implemented this theoretical, this is the mathematical theory, first of all, but for the last years we have been implementing it in an algorithm called William. And recently it has shown it could demonstrate capabilities of machine learning like performances, and it shows that machine learning capabilities can be achieved using data compression. So instead of optimizing various different functions, various different objective functions, we can try to just compress our data and see what happens. And here I have brought with me some examples of outlier detection, centralization, linear regression, and linear classification, and a decision tree in order to exemplify you how it works, because it's not part of the main kind of education about machine learning that what machine learning algorithms do is actually data compression. And I would like to make it more plausible now. So let's take outlier detection, right? You have an array of letters, many A's, and there's somewhere a B in between. And for each letter, you need some bits to describe it, right? And you get a description length, which is denoted by DL below, 244 or so bits you need to describe them. And you can try to represent it in a different way. Say, okay, let's repeat the letter A many times, and then insert the B at the specific index. If you describe it in this way, then you have actually detected the outlier. You have done some data cleaning as well, because you see on the left side there's a string of A's without a B, and that's a cleaned up data set. And we see at the leaves of this tree the description lengths, the sum of the description lengths of the various variables is smaller than the description length of the original data. And you see that you achieve a compression rate of 80%. Here we use the Elias delta code in order to code for integers. You can code floats in a similar way with 2 integers and so on. Have some default description, and then you find a graph, a program graph that actually creates your data, and if its length is smaller, then you have actually compressed. And you see here that compression achieves outlier detection and data cleaning in this simple example. Let's look at a different example, regression. Here you have a y vector and an x vector, as you see in the graph, and x is uniformly distributed between -10 and +10, and you have some ID error, and you have this 2x plus 18 line. And what William does now compresses both x and y. It doesn't care what was the goal. It just compresses every data that it gets. And well, the first thing it does is, okay, why not subtracting a1 from the data? Because then all the data points become smaller, and smaller numbers are actually take fewer bits to describe. So actually centralizing your data is actually compression work. So the next thing is subtracts 2, and at the dashed red line you see our estimate or current estimate of the data. So it approaches, now the next is 4, the next is 16, and you see these shifts are not the result of a specialized compression algorithm, optimization algorithm. It's all done within a unified framework. Nothing special has been done here. And as the next step, it uses the x values in order to subtract them. So now we have the representation essentially x plus some residual error plus 16 equals y. And you see the estimate is getting closer to the data. Now, instead of 1x, we need 2x, and that's what he does in the next step. He adds x twice and adds 17, and still needs one more step, and finally it achieves the perfect fit. And at every step, you see the compression rate increases, and it has achieved perfect description. So there is no minimization of squared errors or something like this. It's just the compression rate. Let's look at a different example. Classification. So here we use the fact that if you have discrete arrays and they consist of, for example, falses and trues, only 2 elements, then a simple way to describe it is just pick an index of all permutations. You look at all permutations with the same number of trues and falses and pick an index. And if the numbers of trues is much less than the falses, then the index, the description of the index will be smaller than if you describe the array bit by bit. And you exploit that. Consider if an x variable is distributed like you see on the right, and the classes are as given by the color, given by the flags true and false. And what would the algorithm do then? Well, it starts to shift the x values first by 1 because, well, that's just compressing. It doesn't know that it does classification. It says, okay, let's centralize my data first because it takes fewer bits to describe. Okay, it does the same, it subtracts 2, subtracts 4 now, and you see the distribution shifts. And then finally, it says, okay, from I test whether the data is smaller than 1, less than 1, and generate a prediction, as you see here. It's also, the prediction will be an array, a Boolean array, and the XOR is essentially a Boolean subtraction. So you have, and the prediction error, as you see, has a much smaller description length than the original class describing array, because there are a few prediction errors. So you see, classification can be also seen as a special case of data compression. So, next, let's look at the decision tree. And we have this classic example from scikit-learn, like you have 3 types of flowers, setosa, versicolor, and virginica, and denoted by by S, C, and V now. And this is given in the class array, and then you have the width of the petals of those flowers. And they are distributed the way as seen on the right, of 0 compression rate in the beginning. And here he finds a simple description. Essentially, it looks like whether the petal width is smaller than 1. And he separates the classes accordingly using this operator insert. You see the third child of insert consists only of the S's of the setosa flowers, which are on the left of the histogram, and the other classes are the third child, where the C's and the V's are, they're on the right side. So, as you remember, usually when finding decision trees, you try to minimize the Gini coefficient, which kind of reduces the diversity of the classes in a group that you have, that you're looking at. But now this is automatically a consequence of compression, because if you have a few number of different values in a list or array, it's just easier to describe. It takes fewer bits to describe. So, and I come to my final remarks, that the generalization of machine learning is possible, as you see in those couple of examples. And in contrast to AutoML, for example, you don't have a heterogeneous set of ready algorithms that you kind of try to select and where you try to just fit some hyperparameters. No, it's just a monolithic single algorithm where the specific machine learning techniques come out as special cases of it. And so we have demonstrated outlier detection, centralization, regression, linear decision tree and decision tree classification here in those examples. these are, of course, simple because it's hard to build these algorithms, right? And as I've demonstrated in different talks, the same algorithm can also do different tasks like perceiving simple geometric figures and playing tic-tac-toe, stuff like that, usually separately, completely other tasks. And immediately, at the same time, there are also no problems like overfitting and out-of-distribution generalization with this approach, because there are no million parameters to tweak and twist. Because compression itself leads to prediction. That's a mathematically proven theorem in Solomonov induction. If you can compress, you can predict best. That's it. So all the problems of out-of-distribution generalization and overfitting solve themselves. They just don't occur. They disappear. And what I would like to finish with is late Marvin Minsky's recommendation, which he said in his last public appearance. He said, study algorithmic information theory. Everybody should learn all about it and spend the rest of their lives working on it. He said it half jokingly, of course, but there is a grain of truth to it. And that's what enables us to pursue this top-down approach to AGI, which you can read more about at our webpage. And on this note, thank you for your attention.
There are no questions from viewers, so a small question from myself. Maybe you'll consider it silly a bit, because it's difficult for me to get into a theory that has so much maths. So imagine you've taught an agent that plays tic-tac-toe. Will that agent be able to learn playing tic-tac-toe on a 4x4 matrix, or will you have to do it from scratch, like in standard reinforcement learning?
So I guess I'll answer in English. No, it's not necessary to do that, because one of our main tenets of our philosophy is not to insert anything task-specific into the algorithm. So like something like the grid size of tic-tac-toe would be a specific thing, right? It works only for tic-tac-toe and only for the 3x3 type tic-tac-toe. And we would not insert that into the algorithm. It would just discover a larger field and would play a larger tic-tac-toe, that's it.
Thank you very much.